We are on the very last lecture of the semester now. And this lecture won't include any new material. It's just going to be a review. And it's a review for those of you who weren't at the last help session or the last recitation section of just the topics since exam 3. For earlier material that was covered by exams 1, 2, and 3, there already are reviews. And I thought it would be better and more efficient to just talk about the new material, so won't talk about the older material. This first part of the lecture notes here, all of this stuff, is an outline of all the topics we've covered since the end of exam 3, so enzyme kinetics and molecular machines. And I won't go over this outline because we're going to go through these topics a little bit, at least one by one. This is mostly to help you or as an aid to your studying. All right, so the very first topic, we didn't cover under exam 3 is enzyme kinetics. Remember, we sort of split kinetics into two parts. One is the general kinetics that we did cover in exam 3, and then the enzyme kinetics that we didn't. Put that off to now, so let's talk about it. So first of all, we talked a little bit about catalysis, because enzymes are catalysts, and so enzyme kinetics is catalytic kinetics. The definition of a catalyst is something that speeds up a reaction, but isn't either consumed or produced in the reaction. So it's something like, if this is your overall reaction, then you add something new, this C for catalyst, but it appears on both sides of the reaction. So if we were doing thermodynamics, you could cancel that C on both sides of the reaction, and the overall reaction would not be changed. The overall reaction would still be just A goes to B, and that's because C doesn't change any of the actual reactants or products. It just changes the rate of reaction. And that means that none of the thermodynamic variables at all, remember, thermodynamics doesn't depend on how fast things go, and it doesn't depend on path. So the mechanism for this reaction with the C present is probably very different than the mechanism for this one. That doesn't matter. Mechanism is path. It doesn't affect the thermodynamics. So delta H, delta S, delta G, equilibrium constants, all the thermodynamic properties are unchanged by the presence of a catalyst. That's an important thing to understand and sort of deeply absorb. For example, it's why you can measure the thermodynamics of metabolism in a complicated organism like us, right? When people measure the rate at which CO2 is produced by your body, it doesn't matter if that CO2 was burned in a fire in a fireplace, or if it was burned by the metabolism inside your body. The routes are totally different in those two cases, right? One's a flame burning in air, the other one is very controlled release of energy inside your cells, but the overall thermodynamics are the same. Path doesn't matter. All right. Catalysts work in general by lowering activation barriers. That means you've got products over here. You've got reactants over here, you've got products over here, and there's a barrier in between an activation energy, and that activation energy gets lowered by the catalyst. And the way that catalyst works is generally by binding to the transition state up here at the top of the barrier, and therefore stabilizing the transition state, and therefore making the transition state, making the barrier smaller. And we saw, I won't dwell on this or redo the calculation, but we saw that relatively modest changes in the barrier height can make enormous differences in the rate of reaction, in the rate constant. And the reason is that the rate constant is proportional to e to the minus, EA over RT, and so the energy, the barrier height is up in the exponential, and that means that it's basically exponentially multiplied or amplified when you make a change in the barrier height. All right. So another point to make is that if the barrier height is lower in this direction, it's also lowered by the equal amount in the opposite direction, and that means that the factor by which the rate constant is sped up when it's catalyzed, so this alpha here, here's the uncatalyzed K, here's the catalyzed K, is the same in both directions. The forward rate and the backward rate are both sped up by the same amount, a factor of 10, let's say, or a factor of 7 or something like that, or a factor of 1,000,000. Yeah, modest barrier changes cause large changes in K, and enzymes very frequently can cause speedups of 1,000,000 and sometimes even more. Some reactions are exceedingly slow without a catalyst and can be exceedingly fast with catalysts, so the amplification factors or the speedup factors can be huge. We looked briefly, I won't go over this in detail because we talked about it in brief in the earlier lectures, but that there are some things called inhomogeneous catalysts, which are basically particles in solution or solid surfaces that that basically stabilize intermediates in some complex reaction pathway. We talked about this reaction being catalyzed on a platinum surface. Let me again warn people that this mechanism is, I don't know that this mechanism is correct. I just put it forward as a plausible one that's useful for illustration purposes. But basically what it means is that all the high energy species, intermediates that would normally cost you a lot of energy to create, are cheaper, are much less costly to create when they're bound to a surface that sticks to those intermediates. And so all these loose hydrogen atoms, for example, and loose OH groups, and possible loose oxygen atoms, and so on, are all at much lower energy. All the intermediates are stabilized, and therefore the activation barrier is much lower. If it's an enzyme, though, it works basically the same way, but looks a little different at least. Very often the enzymes are set up, designed, if you like, to bind to the transition state. They don't bind to the reactant or product, they bind to the transition state. So if you've got a reaction like this, where this guy is going to go to two of these guys, basically this bond is going to get broken in the middle, then the transition state will be something where the bond in the middle is stretched. That would be the high energy state. And when the molecule binds to the enzyme, to the protein, it binds with a little bit of tension on that bond, and so it's basically binding to the transition state or stabilizing the transition state. It's already pre-stretching the bond a little bit. That makes it easier for the bond to finally get broken and produce product. We looked at how this looks for a DNA polymerase. You've got these two catalytic magnesiums. The reaction, the bond that's got to form is between the triphosphate group and the 3' OH group. We looked at DNA polymerases much later, but when we first looked at this example, we hadn't yet looked at the DNA polymerases, so it's good to look at it again. When the transition state is when these charges start to form on the pyrophosphate and on the 3' OH group, which gets deprotonated to form a 3' O- group, basically. And those are high energy processes, but with the 2+ doubly plus divalent cations hanging around, those negative charges are stabilized basically by favorable interactions with the 2+ ions, and that lowers the transition state and therefore makes it easier for the new bond to form, and therefore for the old products to leave. All right, so that's the general picture of catalysis. We could say much more, but good enough for present purposes. Then we talked about the Michaelis-Menten mechanism for enzyme catalysis per se, specifically. And the mechanism can be written out in individual elementary reactions like this, but it's much more common to write it this way, as sort of a flow diagram. The enzyme plus the substrate binds to form an enzyme-substrate complex, or it can go backwards, reverse. So it's a reversible binding. But some part of the time, at least, it goes forward. The substrate gets turned into a product and then released to produce the enzyme again. And the product, the overall reaction, of course, is S goes to P. The presence of S goes to P. The enzyme doesn't change the overall reaction, or the thermodynamics, but it does change the speed at which those things happen. You apply the steady state approximation to this intermediate here, the E enzyme substrate complex, and after a number of steps that we went through, but I won't go through again, you get the Michaelis-Menten rate law, which has two parameters that control how it works. One is Km, the other one is Vmax. Km sets the scale for the substrate. You can see that in this form at least, the velocity only depends on the ratio between the substrate concentration and Km, which means basically that it's the substrate concentration in units of Km that matters. That's what I mean by saying that Km sets the scale for S. When S is equal to Km, the velocity is equal to a half, which tells you that it's the Km value that's setting what the important values or concentrations of S are, the range or order of magnitude over which the enzyme will get saturated and approach its maximum velocity. Then Vmax does the same thing. It sets the scale for the velocity itself, right? If you wanted to, you could rewrite the Michaelis-Menten law in this way, which says that this rescaled velocity is a universal function in this rescaled substrate concentration, right? If you wanted to, yeah, okay, well anyway, that's good enough. Yeah, so the ratio of S to Km determines the ratio of V to Vmax. I said this at the time, but let me just repeat because it's a mistake that happens even at the highest levels, that if you find that your enzyme obeys the Michaelis-Menten mechanism, or sorry, obeys the Michaelis-Menten rate law, that does not mean that it obeys the Michaelis-Menten mechanism. We saw an example of that with the DNA polymerase. The mechanism for the DNA polymerase is much more complicated than the Michaelis-Menten mechanism, and yet the DNA polymerase obeys the Michaelis-Menten rate law. And we saw the reasons for that too. Basically, their steps are too fast to have much effect on the polymerase, on the rates of reaction, on the rates of turnover for the polymerase. All right, you can invert both sides of this rate law, basically 1 over V here and 1 over all of this, and that gives you the expression for the Lightenweaver-Burke plot. It says that if I plot 1 over velocity versus 1 over substrate concentration, I should get a straight line. The slope of that straight line will be Km over Vmax. The intercept of that straight line will be 1 over Vmax. So from one straight line, you can get both of the controlling parameters for the Michaelis-Menten rate law. Vmax is equal to 1 over the intercept, obviously, and Km is equal to the slope divided by the intercept. I said a lot about this when we were talking about it, explaining what both what this means and what the earlier rate law means, but I won't repeat those qualitative things now. I think people are familiar with Michaelis-Menten and Lightenweaver-Burke already to a large extent, and so I won't, since we already I have 29 slides to get through in a reasonable length of time, so we're going to have to go fast. All right, then we talked about the inhibited Michaelis-Menten mechanism. Let me emphasize that this diagram doesn't cover all possible mechanisms of inhibition, but it does cover a pretty wide family of them, so that's a good reason to, and all with a relatively compact and simple addition to the Michaelis-Menten mechanism itself. Basically, 2 branches are added. Branch 1 and branch 2 are type 1 and type 2, one in which the inhibitor binds to the enzyme itself and takes it out of circulation, basically makes there be less effective enzyme in solution. The other one in which the inhibitor binds to the enzyme substrate complex and basically does the same thing. You apply the steady state approximation. Again, other approximations are also needed in this case, and you arrive at this expression for the rate law. The thing that's new, of course, are these alpha and alpha prime numbers, which depend on the inhibitor concentration. So alpha is 1 plus the inhibitor over Ki, and alpha prime is 1 plus the inhibitor over Ki prime. Alpha prime reflects the effects of branch 2, and alpha reflects the effects of branch 1. So now there are 4 parameters in our inhibited Michaelis-Menten mechanism. Km and Vmax are the same and haven't changed, but now there are these 2 Kd values basically for binding by the inhibitor in one place or the other that we also need to find if we want to get the parameters for this model. There is a Lineweaver-Burke plot appropriate for the inhibited case, and when you take 1 over both sides, you see that you get the same kind of plot, 1 over V versus 1 over S, but now the slopes depend on, and the intercepts depend on the inhibitor concentration. So the intercept here depends on the branch 2 inhibition, alpha prime, and the slope here depends on the branch 1 inhibition, that's alpha itself. And so you can tell when inhibition is present, and you can tell when the pure type is present, right? If only the slope changes, then it's pure branch 1. If only the intercept changes as you change the inhibitor concentration, then it's pure branch 2. If both are changing, like in this example, then both branches are active. Let's do a short example. Let's suppose I have two Lineweaver-Burke plots. Well, two curves on a Lineweaver-Burke plot, something like this. In one case, when the inhibitor isn't present, inhibitor is 0, we'll call the intercept for that plot int0, and we give it a value of 0.01 seconds per nanomolar. And it has a slope, which we'll call slope 0, of 0.1 in units of seconds. When the inhibitor is at 10 nanomolar, then the intercept changes. The intercept is now twice what it was before. And the slope also changes. The slope is also twice what it was before. So clearly both branches are operating in this case. And we want to find all 4 of the parameters for this mechanism. So Vmax, parameter number 1 here, is 1 over the intercept. That's 1 over this guy. When the inhibitor is equal to 0, right? So 1 over int 0. Let me put that in here correctly. There we go. And likewise for these, this is slope 0 and int 0. And that's 100 nanomolar per second. So that's the maximum rate at which this enzyme goes in the absence of inhibitor. Km is the slope in the absence of inhibitor divided by the intercept, and that's 0.1 over 0.01, which is 10 nanomolar. So saturation begins to occur when substrate is in the order of nanomolars. The alpha value is equal to, you can see it in the formula up here, right in this. This is the slope, and so if you take the slope when alpha is equal to 1, that is when I is equal to 0, and divide it into the slope when there is inhibitor present, then you get the value of alpha, and in this case that's 0.02 divided by 0.01, which is 2. And therefore Ki, remember, Ki is equal, alpha is equal to 1 plus I over Ki. So solving for Ki gives you I over alpha minus 1, and Ki is therefore 10 nanomolar. Alpha prime is the same thing, but using the intercept here instead of the slope. And again, you get a value of 2 because the intercepts are 0.2 for the inhibited case and 0.1 for the uninhibited case. And again, that gives you a Ki prime of 10 nanomolar. So in this very simple example, the 2 Ks, the 2 Kds are the same value, and that's why both branches are on. That's why both the slope and the intercept were changing at the same time. All right, that's it for enzyme inhibition. The next topic, or the next major topic for this section, was molecular machines. This is mostly qualitative, but it will be the basis, basically, for a lot of application questions in the exam. You can see it in the practice exam. Basically, all the stuff that we learned all semester long can be applied to these machines, And since we spent a fair amount of time in this section talking about molecular machines, most of the questions are oriented towards molecular machines in one form or another. We talked a little bit about what a machine is and gave an example of what it looks like on the macroscopic level, so a car engine basically, or a piston engine. We saw that there's a cycle of steps that the piston goes through, right, that the piston and camshaft go through. And those steps involve putting energy in or putting fuel in, firing the fuel, the generation of motion as a result of firing that fuel, and finally release of products or exhaust, if you like, before the cycle starts over again. So there's fuel involved, yes. The engine does work, torque in this case, in the case of a car engine. It releases heat to the surroundings. It could, in principle, absorb heat from the surroundings, too. There are engines that do that. Car engines generally don't, but things like what's something called a Stirling engine, a very high efficiency engine that's used in a number of settings, do absorb heat from the surroundings. And so, yes, you can see here's the delta G input, that's the fuel and oxygen. Here's a chemical reaction, basically, that takes place. And here's where the heat and work are all done in the rest of the cycle. For a macroscopic engine like this, the fact that these are heavy moving steel parts means that inertia gets generated when forces are acting, and that carries the machine around through the parts of the cycle where forces are not acting anymore, or forces are acting in the opposite direction, in fact. And because it's macroscopic, the system isn't shaking or shivering. Everything's smooth and deterministic, however fast the motor may be going. I mean, some of these motors really go fast, thousands of reps per second, but still, it's smooth on some time scale. All right, now let's look at the microscopic case. We talked about this again. We looked at kinesin in this case, right, which is a little motor that walks hand over hand along a microtubule carrying a cargo of a mitochondrion or some other organelle or fat globule or something like that that it's carrying from one end of a long dendrite, let's say, in a nerve cell to the nucleus, or the other way around. And it goes pretty fast, 700 times per second, typically. What happens in that case? Well, look what the machine cycle looks like in that case. It's a kinetic mechanism. That's what this picture is showing us. It's a kinetic mechanism. So the mechanism of a molecular machine, the kinetic mechanism of a molecular machine, is the machine cycle. And we'll see that again. We saw that when we went through it the first time. We'll see it again in a minute when we're talking about the DNA polymerase. And I won't go through the cycle here, but suffice it to say that a lot of the steps are the same. A lot of the features are the same between the macroscopic and microscopic motors. There's a machine cycle, that's the kinetics. There's fuel, that's the ATP that's coming in. Work gets done when this guy steps and pulls on the cargo. Forces are generated. Those forces are moved through distances, or force times distance is work, so work is being done. And heat is released and absorbed into and out of the surroundings, as shown in this diagram down here. And those also play an important role in the overall thermodynamics of the machine. However, there are some differences. There's no inertia, no significant inertia on the microscopic scale. It isn't that inertia isn't there. The laws of physics says anything that has mass does have inertia, but these are all happening in watery solution, and the water is so viscous on this space scale that inertia just doesn't have a chance to do anything. On the picosecond time scale or shorter, all the inertia damps out, and so everything moves by diffusion, basically by fluctuations or random walk. It doesn't move by inertial motions. And also, everything on the microscopic scale is always shaking and shivering, fluctuating like crazy. And the machine has to be set up or built or designed in order to put up with that. And in fact, most machines require those fluctuations for the very reason that I gave just up above, right? That's the only way they move. They move by fluctuations and diffusion. And if there weren't any of those things, if you cooled the machine down to absolute zero or close, you just freeze the machine in one of its states. It could never transition from one state to another. So There are important differences, there are similarities, but there are also important differences with microscopic molecular machines. Then we began talking about the specific case of DNA polymerases, where we can go into some detail and see how these things worked out. We started addressing first the workings, the basic structure and motions and rates of change and inputs of energy and outputs of energy to the surroundings, all the workings that go into making the machine turn over and do its job. We looked at the structure of the DNA polymerase. There's the thumb and palm and fingers domains. Oops. There we go. And fingers domains. Oh, well, here's fingers over here. That surround the DNA and bind in the minor groove of the DNA here. And surround the growing tip of the DNA, right? Right here is the growing active end of the primer strand, and it's copying the template strand. Here's the template base that's currently being copied. Here's the nucleotide that's currently coming in order to make a new complementary residue on the primer strand. There's the two catalytic magnesiums. We talked about their role just a minute ago, in fact. And there's this triphosphate group that basically provides the energy that drives this whole process forward, and so on. We looked at the kinetic mechanism. It's 5 steps, remember. But remember that the first 2 steps, these two basically, have a rate-limiting step, the fingers closing process, right? These fingers here open and close, and they're open here and here, but they're closed here. So this is the fingers closing step. That fingers closing step is slower than anything else. It's the rate-limiting step. And that means that really only these first 2 steps affect the rate law very much, or the overall rate of reaction very much. These last 3 steps are relatively fast. And so that's why Michaelis-Menten kinetics apply to this much more complicated mechanism than you would think would work with Michaelis-Menten. So we looked at detail, and I won't go over those again. We looked at in some detail at the structures and interactions and motions that occur and are responsible for making each of these steps go. We looked at interactions among the parts. We looked at entropy changes, all those kinds of things. That's too much detail for today, but I encourage people to look that over again, listen to that lecture again, or look over the notes again. Also, we talked about the fact that all these machines generate forces. They have to in order to generate motion, right? If there is no force, then diffusion goes equally in all directions. It will never cause the polymerase to go forward along the DNA, right? Polymerase has got to drive down the DNA and keep inserting new nucleotides. I showed a movie at one point that I didn't paste into this lecture, but it shows the polymerase driving right down the DNA. The only way that can happen is if there's input of energy, and that energy generates forces that push that DNA down the DNA polymerase down the DNA. After all, everything's shivering and shaking. There is no inertia. The polymerase isn't gliding down the DNA. It's being pushed down the DNA in the presence of all kinds of random forces that are trying to make it just sit in one place. And we saw that because there's quite a bit of input energy from the NTP, about 30 kilojoules per mole, actually more than that, 50 kilojoules per mole in a lot of cases, minus 30 kilojoules per mole, and a relatively short distance to move, that means that the maximum force you can generate here, work over distance, so this is something big over something small, is pretty big. 50 piconewtons, that's almost enough to denature the DNA, to pull the DNA right out into a ladder instead of a double helix. At 60 piconewtons, it would do that. I don't know if there are polymerases that actually do that, but it's possible. If you wanted to make a DNA polymerase to generate enough force to actually pull the DNA right out straight, you probably could do it. There's enough energy present to do it anyway. We compared that amount of force to the forces generated by actual motors, these two guys, and yeah. And they're much smaller in the motors, and that's kind of a paradox, but the reason is, of course, that the motors have much bigger step sizes, which means the amount of work they're doing is much greater for a kinesin, the motor we looked at, the stepper we looked up at the top, it generates about 30 kilojoules per mole of work in the course of its process. That's about the same as the work that you put in from the ATP. In other words, the amount of work you're putting out is almost equal to the fuel energy you put in, which means it's got very high efficiency, something like 80 or 90% efficiency. That's not true for the DNA polymerases. Despite the high forces, they move over much shorter distances, and they waste a lot of the energy, at least from the point of view of a motor. Of course, DNA polymerases and RNA polymerases aren't motors, and that's why they don't worry about wasting energy. They're worried about fidelity and other concerns about replicating genomes, not about producing efficient work. All right, then just to return to the kinetic mechanism, we looked at all the actual rates as measured experimentally, all these rates that are in here. And that's where we really saw that, yes, this rate is much slower than the others, and so it's rate limiting. And so this area that's been sort of highlighted in gray here is the Michaelis-Menten part of the mechanism, and all these other steps are fast enough so that they can be at least approximately ignored. They can be ignored, I mean, they obviously can't be ignored from the point of view of a turnover, right? Once you've got here to the closed complex, you've still got to do the catalysis, you've got to release the products, you've got to reopen the fingers, and you've got to translocate the DNA polymerase along the DNA. So there's a whole bunch of stuff that has to happen in order to return to the initial state, but they're all fast enough so that the overall velocity of reaction is not affected much by those. All right, then we looked, one of the things about kinetics is that it depends on reaction barriers, right? The energies of activation. And we looked at the thermodynamics earlier, but we didn't look much at what kinds of things control the energies of activation. I showed just one example because I didn't want to spend all the time going through all of them, and anyway, this is probably the best example, where you can kind of get a feeling. Again, if you know the structure of the polymerase and you know something about the interactions and you know something about thermodynamics, then you can get a rough idea at least what the kinetic barriers are also, and therefore get an estimate or a feeling, a qualitative feeling for what the energy of activation ought to be. And so we saw that in this case, in the fingers closing case, it costs some energy to bend the fingers. You're deforming the fingers. Basically, the fingers is a spring, acting like a spring, and we know how the potential energy changes for a spring. It changes like a harmonic quadratic function. And once the fingers close, they stick to the top of the DNA. We know what a sticking interaction looks like also. It's a narrow, attractive potential energy well. You put those two together and you get something that looks quite a lot like, well, is in fact a reaction energy diagram, where the reaction coordinate that normally exists on a reaction energy diagram is actually the bending angle of the fingers up here. So here's one, I mean, the reason I put this in and the reason I'm reiterating it in this case is because here's one, that reaction coordinate is always mysterious, right? What does that even mean? Well, here, it means a lot of different things in different settings. That's why nobody ever specifies in a freshman level sort of thing, or even in our class, people rarely ever specify what that reaction coordinate is, but it's real. It's not some fake thing. It's not just a random idea. In this case, at least, we can see that it's a concrete geometric variable. It's the bending angle for the fingers. And so we plotted the energy versus this reaction coordinate, this bending angle. And you get a reaction energy diagram with a transition state up here at the top and a certain energy of activation in the forward direction and an energy of activation in the reverse direction and so on. And by looking at the types of interactions and the distances that are involved and so on, you can estimate what the rate of reaction will be over that barrier. Using something called Cramer's theory is probably the best way. It's better than either, well, TST, transition state theory, or I-ring theory just isn't applicable to a system this large, and Arrhenius theory doesn't have the molecular detail to it, so Cramer's theory is the choice. We didn't talk about Cramer's theory, but now you know that name, so if you ever come across a situation like this, you at least have a word for a Google search. All right. And then the overall picture is then that the fingers fluctuate like this. That looks like fluctuations at the bottom of this well. Every once in a while, a fluctuation gets big enough to cause the fingers to come down and stick, and that corresponds to a transition over to the fingers closed state. All right, then we talked about the fidelity of the DNA, and in order to do that, we wanted to look at the thermodynamics of DNA melting because we could compare the delta H for the melting of a correctly paired duplex and the delta S for a correctly paired duplex to the same things for duplexes with mismatches in them. And from the differences between those, we could see how much free energy it cost, or how much delta H and delta S or delta G it cost in order to put a mismatch in place. And in the course of that, we derived this formula, which is a modified Van 't Hoff formula, that says how the melting temperature is and the concentration of DNA single strands in solution is related to the delta H and delta S of melting. We saw that the slope of a plot of 1 over Tm versus log of total concentration over 4 would give you the delta H, and the intercept would give you the delta S. You can change that a little, that formula. I didn't do it in the notes, but I'll do it here. It's a little bit more convenient. You can change this formula into a 2-point formula like we did for Van 't Hoff. And then it looks like this. It looks exactly like Van 't Hoff, except that these are concentrations rather than equilibrium constants, and these are melting temperatures, not just any old temperature. But anyway, if you've got 2 melting temperatures at 2 different concentrations, you can get delta H, and then once you've got delta H, you can use this formula up here again to get delta S. And the result, overall result from these kinds of experiments, melting curve experiments, is that the difference in delta G for a mismatch minus the delta G for a correctly base paired DNA, this delta G value is small, only about 1 kilojoule per mole, maybe 2 kilojoules per mole, depending on the type of mismatch, but not big enough at all to get fidelities of 10 to the 6 or 10 to the 8. We looked briefly at what kinds of things contribute to the delta S and delta H of melting. We saw that the delta S of melting is basically favorable because it releases all these otherwise constrained backbone angles, and there's a certain number of states, associated new rotational states, that become available once the double strand is melted and the DNA becomes single-stranded. And so you're actually able to get a quantitative estimate of what that delta S is using this statistical formula. And we got about 90 kilojoules per mole, which matches very well with the numbers that we'll see in the table down below, in fact. Pay attention to how this calculation was done. Something like this is, well, it's in my mind to be on the exam. I think calculations like this are extremely useful if you go into a research field anyway, if you become a biophysical chemist like me. And so I want to emphasize things that I've found to be very useful in the course of my own career, and this is one of them. All right. Then we also looked at delta H values. These you can't estimate quite so easily. It's kind of ironic that entropy is, most people consider to be very mysterious, but it's easier to estimate in cases like this than the delta H's here. All you can really do is take either experimental numbers or numbers from complicated quantum calculations and things like that to get a feeling for how much energy, how much sticking energy there is when base pairs stack, and how much energy there is when base pairs hydrogen bond like this. We saw the stacking energy is the biggest contribution, about minus 20 kilojoules per mole. And the delta H per H bond is only about -4. That's the net energy change after you've broken the hydrogen bonds to water. So about -8 for an AT and about -12 for a GC. That gives you about 28 kilojoules per mole for a delta H for a single base pair. Well, actually a double base pair like this, actually minus a little bit bigger than that. and a little bit bigger than that for a GC, and that matches very well. Those numbers match, agree qualitatively at least. And the delta S's also agree qualitatively with the numbers in this table, which give the delta H, delta S, and delta G of annealing, remember. This is for the formation of duplexes. For base pairs, for two base pair sequences of different sequence values, of all possible 16 two base pair sequences, counting these identities here. And they all have minus signs because the delta H's are favorable for annealing, remember, and the delta S's are unfavorable for annealing. But notice that the values are actually quite close. We estimated 90, right? It would be minus 90 for annealing up above from the backbone angles, and we estimated, oh, maybe somewhere in the 30s, 35, maybe 36, going higher for GCs like this one, for example. But so we got a very good feeling just from relatively simple considerations for what these values ought to be. All right, we use this also to predict, remember, the melting temperature. I didn't write the formula down. Let me write that formula down here. The melting temperature for, to calculate the delta H of melting and the delta S of melting, of annealing, sorry, from these tables, for some sequence, a former and a tenmer in some of the examples. And then you use those. Tm is equal to delta H of melting over delta S of melting minus R log Ct over 4 to estimate the melting temperatures themselves. And so that's the other quantitative, the Van 't Hoff plots we talked about were one quantitative aspect from this section, and this prediction of melting temperatures is the other one. All right, then we talked about, all right, so thermodynamics doesn't explain the fidelity. What about branch kinetics? We know that, in fact, that's the explanation, or at least that's the official explanation as of this moment. It's always possible for that to change in the future, especially in biophysics, which oftentimes has wrong things embedded in it for long periods of time, decades sometimes. Eventually they get corrected, but they can be wrong for a very long time. So if you see somebody questioning the sort of received wisdom in biophysical chemistry, don't automatically dismiss them. The received wisdom is often wrong in that field because the systems are complicated and hard to investigate. Data is often hard to get and therefore often has serious errors in it. I can give you stories from that kind of thing from my own experience. Anyway, branch kinetics we talked about earlier in the general kinetics section. We talked about the fact that if you've got a single reactant going to two different products with different rate constants, and then you wait till time goes to infinity, till all the reactant is used up and you've got nothing but products, and ask what's the ratio of products that you get, it's equal to the ratio of rate constants. So if K1 is fast, you're going to get a lot of B, but if K2 is fast, you're going to get a lot of C. I didn't say it at the time. In fact, I've never said it before this, but let me point out that this is also true for the rate of production at steady state. In other words, you don't have to consider a situation where you're using up all of the reactant. You can just consider a situation where you're putting in new reactant all the time and creating new product all the time in a steady state situation, a sort of fuel cell situation. And then the rate of production of B over the rate of production of C also is equal to the ratio of the rate constants. If K1 is 10 times faster, you'll produce B 10 times faster than you produce C. That's really more relevant to the DNA polymerase case, since we usually don't allow the DNA polymerase to go to completion, right? The reaction doesn't go to completion. It operates at a steady state most of the time. So this is really the relevant relationship. All right, so this is exactly what applies to the DNA polymerase. You've got a protein DNA complex. It binds an NTP, a good NTP, and it goes fast, 300 cycles per second, roughly. It binds a bad NTP, though, and it goes slow. It can bind an NTP, and it can even incorporate it, but it goes slow. And that means that if you're operating at steady state, you're going to get, this ratio, 300 over 0.03, which is 10,000. You're going to get 10,000 times more of the good stuff over the bad stuff, which means that you're going to get an error once every 10,000 nucleotides or so. And I said that that's great, but not good enough. It's got to be better because you've got to make only about one mistake per replication of the genome. And that means that you can only replicate genomes of about 10,000 bases with this level, with fidelity of 10 to the 4. That's good enough for viruses. But viruses aren't even alive. It's not good enough even for a bacterium. Certainly not good enough for us. So you got to do better than that. The answer to that is proofreading down here. We talked about that, and I'll come back to that in a second. But before we do that, let's talk about why the bad NTP is so slow. And the answer is that basically when the mismatch comes in, it's got the wrong size and the wrong shape and the wrong angles that its connections to the backbone make. The two good, correct nucleotides, AT and GC, have very close angles in their connections to the backbone. They have very similar sizes, and they have very similar shapes, so that they can be, both of them can work. But all the mismatches have either bad shape or bad angles or bad size or all three. And that affects the KM and the KCAT. The KM because it prevents bad nucleotides from sticking in the first place, from binding in the binding pocket and then the fingers closing in the first place. And it affects the KCAT because, again, yes, it also slows the fingers down from binding. The KM is the bigger effect. It creates effects of thousands, advantages of 1,000 for the correct nucleotide of thousands, and the KCAT effect is smaller, between 4 and 8. All right, proofreading again means that while the DNA is plowing along, DNA polymerase is plowing along, putting in correct nucleotides, if it puts in a bad nucleotide and it actually gets in, so the bad nucleotide is here, it's in the bad place, or the bad base pair is there, then the next nucleotide you're trying to put in is really slow, which gives lots of time for the DNA to shift over to this exonuclease site, and that exonuclease site will cut out the bad nucleotide. And so slow processes cause the exo site to cut out bad base pairs, and that's called proofreading. The overall effect we talked about just last lecture, so I won't go over it here again, but if there aren't any mismatches, you're going fast, right? Fast steps here, fast steps there. The proofreading domain is also relatively fast, but still 10 times slower in the numbers I put here than the actual correct replication, which means that you're chewing back or spitting out or undoing about 10% of your good nucleotides, but that's okay. That's not too big a price to pay. But on the other hand, if you're going in on the mismatch side, first of all, it's very slow to start with, and then the next step after that is also very slow, which is what you need in order to get the mismatch really stuck into the DNA, right? The DNA, once you've got two nucleotides in place, a bad one here, and then the next one after that, once you've got both of those in place, then that mismatch is really part of the DNA. But it takes both steps, not just one, because otherwise the proofreader may get it. And both of them are slow, which means the overall rate for this mismatch, this pure mismatch branch, is very slow compared to, well, the proofreading rate now is 30 times faster with these numbers than the mismatch solidification step, which means you end up going back here, which means you have a chance to go back down the good path. That is enough to give us the fidelity we need for at least for bacteria and also for our own genomes. And that is the end of this review. I didn't do any looking over of the practice exam or going through the practice exam. I'll do that in lectures that I will start putting out hopefully maybe tomorrow or over the weekend. And hopefully that will be a help for studying for the final. Let me just remind everybody that the final is, I should have put this at the beginning, the final is Friday the 11th of December between 8 p.m. and 10 p.m. So the time is the same as all the exams, and the Friday 11th of December is also the time that was scheduled for the final in the final schedule, the final exam schedule.